In the previous lesson, you learned about some normal causes of battery aging and degradation, and now we're going to look at what happens to a battery cell when it is abused. Some bad things to do to a battery cell include overcharging it or undercharging it or subjecting it to temperatures that are too high. And when I'm talking about overcharge and undercharge and overtemperature, I can be referring to what's happening to the entire cell, but the real problem really is what's happening locally at some point internal to that cell. So it's possible actually to have local overcharge or undercharge or overtemperature at some point in the cell when it may not be obvious that this is happening by simply looking at what's happening measured outside of the cell. And that's one reason why present-day battery management system algorithms are conservative in how a battery pack is operated, and how perhaps some physics-based methods in the future might be able to extend that operating range to give more performance. If we violate a temperature or a voltage specification, that can cause a number of things to happen. One of them might be electrolyte breakdown. One of them might be electrode plating, or we could have penetration of the separator where one electrode contacts the other, or we could have gases forming or swelling of the packaging and even venting of the packaging. We can even have overheating and thermal runaway. And you've seen some of these before in the previous lesson and when we talked about thermal management, but here we're talking about them in an extreme way due to some abuse. Most of these conditions, one way or another, end up with the cell overheating, and that's what ultimately causes it to fail. In addition to all of those things, mechanical or physical abuse is also a bad thing. Physical abuse of a battery cell might include dropping it or crushing it or penetrating the package or impacting it or immersing it in fluids or freezing it or placing it in contact with fire. Any of these things could appear in an automotive battery pack. So for example, if a vehicle is involved in an accident, the battery pack could be physically damaged in severe ways. And so the photograph on this slide I thought was really interesting. It's an early electric vehicle that has been obviously in a minor traffic accident. And unfortunately, the early electric vehicles did not catch on because the lead-acid battery cells of the time were not capable of supplying the kind of range needed and could not compete against gasoline vehicles. But today we're seeing a comeback that I'm very excited about. And so even though electric vehicles took a vacation for about 100 years, I think that we'll see more and more of them on the road. So when your battery pack encounters some kind of physical abuse, it's generally accepted that the battery pack is not required to survive these trials and still be perfectly operational. But the battery pack itself should not cause an increased hazard to the user, to the person who is perhaps driving the vehicle, if the battery pack is subjected to any of these physical abuses. When a battery ages normally, or when it's abused and ultimately fails, one of three different failure modes will become apparent, and it's generally not possible to predict in advance which one will occur. It depends very much on the circumstances of the failure. The first type of failure mode is that of open circuit. This is in some ways the safest of all of the different modes of failure, but it might not be the safest for the application. That is, it's the safest for the cell, but not for the application necessarily. So I've drawn a knife switch here in the open position, and you can imagine your battery cell coming to the same condition, that instead of supplying a voltage, supplying energy to the load, instead it opens up a circuit. It causes an infinite resistance between the two terminals of the cell and no voltage being generated by this cell. So once this current path is cut by the internal open circuit, the cell is isolated and the possibility of further damage to this cell is very limited. But if I have a whole lot of series connected battery cells in my battery pack and one of the cells fails in an open circuit condition, then the whole battery pack is open circuit even though all of the other cells may be perfectly healthy and the battery pack is no longer able to provide power. The second failure mode is due to an internal short circuit, and there are two varieties of short circuit that are often talked about. One is what we call a hard short circuit, where a solid connection is formed between the positive and negative electrode of the cell, and this allows an extremely high level of current to flow the moment that the short circuit occurs, and it completely discharges the battery cell and results in permanent damage to this cell. The second type of short circuit is called a soft short, and this happens when there is localized contact between the electrodes somewhere internal to the battery cell, but not global contact, and really a fairly high resistance local contact even. In some cases, this is self-correcting because locally the battery cell heats up and it might melt the separator material and then eliminate the contact between the two electrodes as the separator fills that area. Other times the short circuit results in simply an elevated rate of self-discharge, but where the battery cell is still fairly functional. It still can be charged and it can still deliver energy to the load. It just has a self-discharge rate that's much higher perhaps than the other cells in a battery pack. In either case, in either the hard short or the soft short case, a battery pack, if it's kept cool enough when the short circuit event occurs, may not enter thermal runaway. The cell itself will eventually or quickly discharge down to 0 volts, but will still be able to conduct current. And if the battery cell can be drawn down to 0 volts safely, then a series-connected battery pack is still able to conduct current through it because the one cell is acting just like a resistor at that point. It can't really charge it, can't really discharge it. It increases the resistance of your battery pack. It slightly reduces the voltage of your battery pack because that cell does not produce voltage any longer, but you can still operate your device. So in that case, the soft short circuit can be more desirable than the open circuit in some applications. The picture on this slide shows some steps in a process where we can see aging of different causes happening, that maybe there's some SEI formation after the cell is formed, and maybe this SEI decomposes and has some products in it that lead to dissolution of the copper current collector, and then we're starting to cycle copper through the battery cell in addition to trying to cycle lithium through the battery cell, and this can cause metal dendrites to form that join the electrodes together, which can lead to a mild internal short with very thin dendrites that have a very high resistance. But if this keeps on happening, we form thicker and thicker short circuit wiring, if you will, with these dendrites penetrating the separator that can lead to moderate and severe short circuits as well. The third failure mode after open circuit and short circuit is most severe. It's a fire or an explosion. And you might know from your background in chemistry that the rate of most chemical reactions tends to double for every 10 degrees Celsius increase in temperature. So if the heat produced by a short circuit or some other failure cannot be removed as quickly as it's generated, then this can set up a self-sustaining and uncontrolled positive feedback loop known as thermal runaway. The generated heat causes the temperature to increase. The temperature increase causes the cause of temperature increase to be generated more quickly, so there's more heat generated more quickly. And so this spirals until there's a resulting fire and sometimes an explosion. Of course, we must avoid this if at all possible. So in this short lesson, you've learned that cells can fail due to improper controls. They can also fail due to physical abuse. The failures manifest themselves externally either as open circuit or short circuit and/or a thermal runaway event. And we must take every precaution to avoid increased safety hazards by putting in protection mechanisms on our battery packs, by carefully building the battery pack enclosures to protect the enclosures themselves from penetration and crushing and so forth, and many other things. So there's a lot of engineering analysis and design that goes into the construction of a battery pack in order to protect the user as much as possible. But our focus is on algorithms for battery management and control, and I think it's about time that we started to move on and look at that in much more detail. So this brings us to the end of the content of this bonus honors week of the course. There's one more lesson that summarizes everything and then points you forward into the second course in the specialization, and that's what we'll do next, but get prepared. The next step after that is course number 2.